Okay, so we're going to talk about 12.2, which is exponential functions. So this is what an exponential function looks like. F of x, because as we're talking about functions, equals a to the x. Okay, so a is called the base, and x is called the power, or exponent. Okay, and we have some restrictions on what a can be. Right, it's going to be a real number, no i's involved. It cannot be 1, because that's not very interesting. And we'll require it to be positive. It can't be negative, no negative numbers for a base. Okay, so let's go ahead and take a look at this exponential function. F of x equals 2 to the x. And since it's new to us, right, graphing exponential functions, we'll start with a table. Let's see if we can get a handle on what it should look like. So we'll plug in some x values and see what y is. And I just want to remind you how all that works. So if x is negative 2, the way that would look, we'd say, okay, we'll find f of negative 2. And that is my base 2 raised to this value, negative 2. And what do negative signs and exponents do? Exactly, they take that base, we get its reciprocal, power is now positive, so 1 over 2 to the positive 2, also known as 1/4. So if you need to go back and review your exponent properties, this would be a great time. I think you'll find them in Chapter 4. So you can always go to the study plan in My Math Lab. So you go to My Math Lab, find the study plan. You have to open up a big collapsed folder. I think it says See All Chapters. And then just go find Chapter 4. Okay, and you can practice on exponent properties. Okay, so f of negative 1, 2 to the negative 1 would be 1/2. 2 to the 0, right, anything to the 0 is 1. 2 to the first, 2 to the second. Okay, here's another tricky one, 1/2. What does 2 to the 1/2 mean? Did we remember that exponent property? So what do we do if we have a rational exponent? Remember, that was just another way to write radicals. So my base is the radicand, 2 is the radicand, and then the exponent, right, the denominator was the index, and the numerator is what we raised it to. So 2 to the 1/2 is, right, just another way to write the square root of 2. And the square root of 2, it's irrational, so it doesn't really end at 1.4, but that's close enough for my graph. Okay, so I'll call it 1.4 for now. Well, let's go plot these points and see what they look like. So at x is negative 2, my y value is 1/4. Okay, and at x is negative 1, my y value is 1/2. X is 0, y is 1, x is 1, y is 2, x is 2, y is 4. What do you suppose? If x is 3, what's y? Right, 8, so all the way up there. Okay, does it look like those are falling in line? Well, maybe not in line, but a smooth curve that we could draw to connect them all? Yeah, me too. Do you suppose it goes on forever out that way? Yeah. How about forever out this way towards negative infinity for my x's? Yeah, and it's just going to keep getting closer and closer to that y-axis. It's not going to touch it though, and think about why not. Why can I never get to, right, I'm sorry, my x-axis. Why can I never get to my x-axis? Well, right, I'd have to get a y value. I'd have to find a solution to this. If I had an x-intercept, I'd need a solution to the equation 2 to the x equals 0. And there's really nothing you can do in an exponent that'll change this value to 0. Right, so that one, I never get those. Okay, so this is just our generic graph. So now let's talk about the domain. What kind of x's did we plug in? Positives, negatives, fractions, right? We did them all. So the domain is all real numbers, which in interval notation, remember, we write like this: negative infinity to positive infinity with parentheses. My range, remember range y values, and you'll notice I do not have any negative y values. In fact, I don't even have 0. But when we write it, we do start at 0, but we put a parenthesis that says not including. And then my y values go on forever. Okay, so in infinity. Okay, so some general sketches. So f of x equals a to the x if a is greater than 1. It looks just like that picture we drew. And the bigger a is, right? So the bigger the base, the steeper your graph is going to be. Now, if I have g of x equals a to the x, but this time if I restrict a to being a fraction, so some value between 0 and 1, then it's the same graph we just had, just reflected over the y-axis. So it starts high and gets small. Okay. The domain and range, right, still the same. All real numbers for my domain, and my range is from 0 to infinity. Okay, so we're going to do a little Wayback Machine. You don't have to set the Wayback Machine very far, just chapter 11. Remember when we shifted our quadratic functions? F of x equals x minus 2 squared plus 3. Right? So it's a quadratic shifted right 2 and then up 3. So I'd go right 2, up 3, and right, we've shifted the vertex from here, right 2, up 3, and then just draw your parabola. Oh, that's a pretty lame parabola. Sorry. Okay. Well, we're going to do the same thing with our exponential functions, but we just don't have that much to move. Okay. I'm going to bring back my other picture. I want to give one more vocabulary word. So our picture right here, our 2 to the x, we call this, the fact that we're getting super close to our x-axis but never touching, we call that an asymp, A-S-Y-M-P, tote, an asymptote. Okay. And it's this line, so an asymptote is a line. Our graph gets closer and closer to. Okay, so we have this asymptote. Okay, I'm going to go ahead and move that. So back to page 2. So we're going to do that same shifting thing with our exponential functions. However, we don't have that much to move. So it's kind of hard to get anchors on these. So what I will move as my anchors are, I'm going to move my y-intercept. Remember that used to be at 0, 1. So I'm going to move that. And I'm going to move my asymptote. That used to be the x-axis. Okay, so let's take a look at this guy. Y equals 2 to the x plus 3. So y equals 2 to the x gives me my basic shape. And then what I've done to it is shifted it up 3. Okay, so I'll do my basic shape in a dotted blue line, and my purple pen looks about the same, but that's okay. So now I'm going to take and shift this point up 3. 1, 2, 3. Okay, and all the points get shifted up 3. It's just hard to see all of them, right? But this one here would go up 3 steps. 1, 2, 3. My asymptote that used to be over here, I need to move that up 3 as well. So 1, 2, 3. And I'll do a dotted line here for that asymptote. And then I'm just going to draw my shape. Okay, so this gap should be a constant 3 for all of those points. All right, so what's my domain? What x's do we use? I know, it's weird, isn't it? All of them. Plug any value of x in there, it doesn't matter. What y's do we get out? Right? I don't get a y value of 1 anymore, or 2, or 3. I do have a y value of 4. 1, 2, 3, 4, right? That 4 is my 0, 4 is my y-intercept. But I can't get below 3, right? So it used to be here at the x-axis, that got moved up 3, so my new range is going to be 3 to infinity. So it used to be 0 to infinity for my unshifted, and I've shifted that up 3, so the 0 moves up 3. Okay, I have an example, and then I'm going to have to go grab a calculator. So compounded interest. Okay. Hey, the good news, in almost all of the word problems that I saw in my math lab, they give you the formula. We don't have to do a whole lot of extra work. Okay, we just have to use it correctly. So here we go. Compound interest formula. A equals P times the quantity, 1 plus R over N raised to the NT. So compounded interest, right, that's where you earn interest on your interest. And interest is the money the bank pays you for the privilege of them keeping your money and doing stuff with it. They don't pay very much these days. Okay, so A stands for our account balance, how much we have at any given time. P is our principal, what we start with. Okay, how much you start investing. And by the way, this formula, it works for loans as well. Okay, so it works if you're investing money or if you're borrowing money, same formula. R is the interest rate, the annual interest rate in decimal form. N is the number of times of compounding per year. Year. And T is the number of years. So if it compounds quarterly, N is 4. Annually, N is 1. Monthly, N is 12, right? Those are some of the common ones you might see. Okay, so let's go ahead and give it a try here on page 3. So if $3,000 is invested at 6% compounded annually, find a formula that gives the amount we have T years later. So let's start with that. And then how much will be in the account 5 years later. So first we have to come up with the formula. So the generic A equals P times 1 plus R over N raised to the N times T. What does everybody stand for? All right, so we want our equation to be A equals, we're keeping that. P is what we start with. Right, 3,000. And then we start our parentheses. 1 plus the interest rate. So it's 6%, so we make that into a decimal. So 0.06 divided by N. Let's see, we're compounding annually, so that would be a 1. And then the exponent is N times T. Okay, so this is a formula that gives the amount we have T years later. So I'll go ahead and clean that up before I put a circle around it. So 3,000, 1 plus 0.06 over 1, well that's just 1.06, right? And then 1 times T is just T. Well, that cleaned up very nicely. Okay, so there's my formula that will tell me how much I have at any time in the future. So now the second part, the second sentence says, hey, find how much would be in the account 5 years later. So A equals 3,000 times 1.06 to the 5th. Okay, I don't have a calculator. Hold on, I'm going to go grab one. Okay, I'm back with a calculator. I know I paused it. You didn't even know I was gone. Okay, so I'm going to go ahead and punch that in. I have a graphing calculator. I'll put it here on the screen. So if you don't have a graphing calculator, you're not supposed to. Don't worry about that. But if you do, this is what it looks like. So I can just do 3,000. Oh, you can't even see that. Let me try this. Turn off I have some adjustments here. So there's 3,000 and then times 1.06 to the 5th. So depending on your calculator, you might need to do your 1.06 to the 5th first, get that result, and then multiply it by the 3,000. But hopefully, you can make your calculators tell you, and it's dollars, so I'll go ahead and put my dollar symbol, 4014.6, and I'll round to cents, and then I'd round it up, 8. Okay, So that's the answer to the second part. We just plug the value in for t. Okay, so here's the last example. A new phone loses 70% of its value every year. If a new iPhone runs $700, that's about right, find a formula that gives the value at time t. So V of t equals, I need something to go in here, times 0.7t. Right, so here's how much it's losing every time, and it loses that off of its initial value. So 700 times 0.07t. So if you compare this formula to the one we just found, okay, we have our initial amount, and this is greater than 1, and our account's getting bigger, right? I have more right after 5 years than I started with. On this, right, on our iPhone example, here's my initial amount, but this number is less than 1. Okay? So that's going to decrease the value of my phone each year. So what is the value of the phone after 3 years? Well, there we go. Plug in a 3. Right, so we're just finding, V of 3. So 700 times 0.7 to the third. I'm just punching it into my calculator right now. $240.10. Okay. Great. Hey, is that phone ever worth nothing? Is it ever worth $0? And why not? Okay, maybe if you drop it in the ocean. But technically, it's never worth 0 because there's nothing I can do with an exponent that will make my value equal to 0. Okay, here's something for you to think about. So we start at t equals 0, it's worth 700. Here's my base, 0.7. It's a number between 0 and 1, right? So its graph, and I don't have to draw the left side because I don't know what happened before my phone came into being. Right? But it's that flipped over exponential function. And I have this asymptote now with the positive x-axis. So it heads down towards it, but it never gets there. Okay, so good luck on the word problems. Remember, just take a deep breath because they're going to give you the formula most of the time.